Hello everyone, and welcome to Calculus Lesson 8.2, Equations of Planes. The first thing I want to do is actually look at the investigation at the beginning of section 8.2 on pages 441 to 444. So I'm going to bring that up on the screen now. Okay, so if you have your book in front of you or you have the electronic version, just take a look. So we're going to start off the investigation with number 1. So what we saw in 8.1 is how to express a line using vector and scalar equations. Now, we saw that a line you cannot represent with a scalar equation in three-dimensional space. And that three-dimensional scalar equation is actually the equation of a two-dimensional surface, so a plane. And that's what this looks like. So a plane, you can imagine it like a flat piece of paper that extends infinitely in all directions. The reason why you only have a finite rectangle or square here is, well, because they're not going to draw an infinite two-dimensional shape. But that's the idea. It extends on infinitely in all directions. So the first thing it says is consider these planes. So in part I, take a look at the points on these planes. And in part II, look at the points. So just take a moment. You can pause the video if you'd like and just study it and see if there's something unique about it. Okay, if we go to image 3, again, take a moment, pause the video if you'd like, take a look at that plane and see if there's anything specifically interesting about it. Okay. Pause the video again if you need a couple more moments. But let's go ahead into the solution here. In this first part I, what I notice is that all of the planes have the same x value, but the y and the z values are different. So they all have the x value, x is equal to 3. Now, if you recall, and this is actually here in the blurb, this is actually pretty informative. If you have a line and it's x is equal to 5, you know that that's a vertical line. And that means that for every point on the line, they all have the same x value of 5. The y values are different, but the x values will always be this. So similarly here, all the x values are always 3. It's just the y and the z values that can change. That means that most likely I can represent this plane with a simple expression, x is equal to 3. We'll get to the equations afterward, but just keep that in your mind. If we look at box 2, we can see that something that they all have in common is the y value. They all have the y value of 3. And sure enough, if you actually look at that plane, it looks like a sheet of paper that is cutting the y-axis at y is equal to 3. And sure enough, you can see here the y-intercept. Well, not the y-intercept, but the point on the y-axis. Similarly, for the x-plane, we've got the plane cutting the x-axis at x is equal to 3. Now, if you look at the last image here, we've got the z. So you've got z is equal to 3, z is equal to 3 for all the points. And so this is essentially a plane that is, or a sheet of paper that is cutting the positive z-axis at 3. Okay, so that's what they all have in common. Okay, so then part B, reflect, which equation do you think defines each plane? Well, we just went over that in the first part. X is equal to 3 most likely points to a plane where all the x values are 3 and the y and z values can be different. Y is equal to 3. That's a plane where all the y values have to be 3 and the x and z values are different. And likewise, z is equal to 3. That would be the last one. All the z values must always be 3. The x and y values change. Okay. Describe each plane in words. Well, we did that. It's essentially a sheet of paper that's cutting either the z, the y, or the x-axis at a particular value. Okay, for number 2, repeat step 1 for these 6 planes. We're going to go ahead and skip this. I think it's very much the same. If you want, you can pause it and take a look. But for z is equal to -2, there it is. All the z values are -2. X is equal to 6, there it is. And x is equal to 2, there it is. Okay, so all the x values are the same, and at the bottom here, all the z values are the same. Number 3, how would you describe a plane with an equation y is equal to 6? Okay, so same idea. If you have y is equal to 6, that means every single point on the plane, and there are infinitely many points, they all have to have the y value of 6. The x and z values can be different, but that's beside the point. So to list the coordinates of 6 points on the plane, you can come up with any value for x and z and just make sure that the y value is always 6. So for example, let's go back to the sheet of paper here. 6 examples of points. So this was number 3, I believe. So 6 sets of points. So let's see, there's 1, 2, 3, 4, 5, and 6. Okay. So again, they all have to have the y value of 6. And you can fill in whatever you want for the x and the z. So I can put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just filling in random numbers here. I can make some of those x values negative. I can make some of those, oh, let's put there, 11. I can make some of the z values negative. Okay. It doesn't matter as long as all the y values are negative 6. Oh, and I missed another one there, 12. Okay, so there are 12 points, and well, there are infinitely many, like I said, that you could possibly choose. All right, let's go back to the investigation. Number 4, how does each plane change for different values of k? Okay, so if x is equal to k, we saw this again earlier, this is a plane that is cutting. Imagine a piece of paper that cuts the x-axis at this value, k. So if k is equal to negative 7, that means it's a piece of paper cutting the x-axis at negative 7. Okay, the same for y and the same for z. They're cutting each of the axes at their respective k values. All right, number 5. Consider these planes. What do all the points on each plane have in common? Now I really want you to take a minute or two, just pause the video and figure out what they have in common. Okay, we'll resume in a few seconds. So hopefully you pause the video. If you haven't paused it, pause it now and try to figure this out. If you've already unpaused it, this is what we're looking at here. When I look at the points on this plane, something that immediately sticks out to me is that I see -2, -2, and then 3. -1, -1, then 3. 0, 0, 1. Okay, so there is no pattern with these z values. -2, -2, 3. What you should notice is that the x and the y values are always the same, but the z value just changes depending on where the point is. 2.4, 2.4, 1, 1. If you look at part II, it's similar yet a little different. 2, -2, 2, 0, 0, 0, -2, 2, 0, -2, 2, -2. This one might be a little bit harder to see, but if you take a close look, the x and y values are the same magnitude but opposite sign, and the z value just happens to be different. So even though the z values are always 2, -2, or 0, that's not really relevant here. It's just that the x and y values are always negatives of each other. You could have a z value somewhere completely different. Okay. Which equation do you think defines each plane? Okay, so x plus y equals to 0. Well, we just said that for the plane in I said that the x and y values are equal to each other. So let's just go back to the sheet here. So this is for 5. So for I, we said that the x values and the y values are the same. For part II, we said that the x values were the negative of the y values. Now, if I just rearrange these equations, for I get x minus y is equal to 0, and for I get x plus y is equal to 0. Right, so let's go back to our textbook here. And sure enough, that's what we see here. In I, we have x plus y is 0. That means this matches the plane in II. And the equation II, this connects to the graph I. Okay. Describe each plane in words. Okay, so to describe the plane in words, you would state that this plane in part I, the x and y values are always the same. The z value changes. Okay, for II, how do we describe this plane? The x and y values are always negatives of each other. Same magnitude, z value will change. Okay. Let's see, number 6, consider these planes and their equations. how do the points shown on each plane relate to the equation on the plane? Well, think about the equation of a line. If you have a line and you have the equation of the line, any value you plug in to the x component into the input of the equation, you will get the corresponding y value on the line. So it makes sense that if you have the equation of a plane, if you were to plug in some x value, you should get the corresponding y value out. After all, this equation only has 2 variables, not 3. It just has x and y. So if I plug in, let's see, an x value of 0, okay, then my y value should be what? So think about that for a second. Okay, so go back to your screen. So this is 6a. So if I have x minus y is equal to 3, if you plug in, let's say x is equal to 0, 0 minus y is equal to 3, so y is equal to -3. So that's the corresponding y value. Now, I know that that relationship has to hold for x and y. How do I find z? Well, that's going to be an extra step. I don't yet have any way of finding the z values, and you can actually see here that the z values are changing, but I at least know a relationship between x and y, and that's true for both a and b. So what I really want you to get out of this investigation is just how can plane equations be formed? How do the planes look like? And well, how do you visualize them in 3-dimensional space? So try to visualize them as pieces of paper, but just remember that they extend infinitely in all directions. So we're going to go back to our formal lesson now. We're going to try our first example. And this time we're going to add an extra dimension to our plane equation. So example 1, consider the plane defined by the scalar equation x plus 2y minus z minus 8 is equal to 0. So for part A, determine if the points A, so 1, 3, -1, B, which is 3, 5, 1, and C, 1, 6, 5, are on the plane. Okay, so this really isn't too bad. Okay, so think about this. Let's say, just for example's sake, if you had the line y is equal to 4x minus 7, for example, okay, and if you were asked if the point 1, 2 was on the line, what would you do? Well, you would take the x value, you would plug it in and see if you got the y value of 2, or you would plug in the y value and see if you obtain the x value. Overall, you would see if left side equals right side. And we do the exact same thing here. We just have to check these points. We've got the formula. So you just have to make sure that left side equals right side. Okay. Now, the right side in this equation is always 0, so that's pretty simple. Okay, so let's check A first. A is 1, 3, minus 1. So left side, I have x plus 2y minus z minus 8. All right, so my x is 1, my y is 3, and my z is -1. So watch that minus -1 there. Okay. So we have 1 plus 6 plus 1 minus 8. 6 and 1 makes 8. Minus 8 is 0, which is equal to the right side. So therefore, A is on the plane. Okay. Now we're going to check B, which is 3, 5, 1. By the way, feel free to pause the video at any time and try these on your own, and then you can always fast forward the video and see where you're at. Left side. Okay. x plus 2y minus z minus 8. So x is 3 plus 2 times 5 minus 1 minus 8. All right, so that's 3 plus 10 minus 1 minus 8, which is minus 9. 10 minus 9 is 1. 1 and 3 makes 4. Okay. So that's 4. That does not equal 0, which is the right side. Therefore, B is not on the plane. Okay. We have to do the same thing for C. I'm not going to go through the full solution because at this point I think that you can see how we do this. So go ahead, pause the video and try this one on your own. I'll wait a few seconds before I tell you the final result. Okay, so if we plug in our values here, you are going to get that the left side is equal to 0, which is equal to the right side, and therefore C is on the plane. Okay, I hope that's okay. Let's move on to part B. Now, just as lines have intercepts, they can have x, y, and z intercepts if you're considering R3, planes also cut those intercepts. So they can also have x, y, and z intercepts. So let's take a look at that. Part B. Determine the x, y, and z intercepts of the plane. Again, use your analogy with lines. If you had a straight line and you were looking for the x-intercept, you would set the y value equal to 0. And likewise, if you were looking for the y-intercept, you would set the x value equal to 0. Okay, so same idea. So if we're looking for the x-intercept, we just have to remember that we're in 3 dimensions now, not 2. So we have x, y, and z. If I'm looking for the x-intercept, I not only have to set y equal to 0, I must also set z equal to 0. Okay, so I have the equation of the plane. It's x plus 2y minus z minus 8 is equal to 0. So I just have to plug y and z to be 0. So that's x plus 2 times 0 minus 0 minus 8 is equal to 0. So 2 times 0, that's 0, and 0 is 0. So we have x minus 8 is equal to 0. X is equal to 8. So that's the x-intercept. All right. Y-intercept, same thing. We're going to set x equal to 0 and z equal to 0. All right, so our equation, x plus 2y minus z minus 8 is equal to 0. If we plug in 0 for x and 0 for y, we're going to end up with 2y minus 8 is equal to 0. 2y is equal to 8. Y is equal to 4. Now, I'm sure you can see that it's going to be the same steps to find the z-intercept. You're going to set x is equal to 0, y is equal to 0. Pause the video for a second and figure out what the z-intercept is. Okay. After your calculation, you should find that the z-intercept is z is equal to -8. Okay. So that's part B. Part C, determine the coordinates of another point on the plane. Okay, if you had the equation of a straight line, how would you find the coordinates of another point on the line? Well, you would just plug in any x value within the domain and figure out the corresponding y value. Now this time I don't have 2 variables, x and y, I have 3, x, y, and z. So I have to input one less dimension than I know and figure out what the resulting unknown dimension is. So if I have x, y, and z as my dimensions, I can plug in any value for x and y and then figure out what the corresponding value for z would be. All right, so For example, okay, let's let x equal 1. Let's let y equal 2, and we'll find the equation for, or rather the value for z. All right, so here's our equation. X plus 2y minus z minus 8 is equal to 0. Okay, so x is 1, y is 2, minus z minus 8. Okay, so this way you're not forcing the point, because then you wouldn't know if it exists, but by just setting values for x and y, I can find the resulting unknown dimension. So here I have 1 plus 4 minus z minus 8 is 0. 1 and 4 makes 5, minus 8 is negative 3. So negative 3 minus z equals to 0. So z is equal to negative 3. Okay, so that means, therefore, 1, 2, negative 3 is a point on the plane. And most likely, if you were doing this, let's say on a quiz or a test, you would all get different points depending on what values you plugged in. Although now that I think about it, most likely you might get similar points because we have a tendency to plug in smaller values to make our job a little easier, which is fine. All right. Part D. Write two vectors that are parallel to the plane. Okay. So in order to understand this, let's go back to, well, part A of the problem. In part A, we saw that we had 3 points. We have A, B, and C. We had to determine if they were on the plane. And what we found was that A and C were on the plane, but B was not. Okay? A and C are on the plane, but B is not. So if we were to sketch this, just imagine you have some two-dimensional surface. I have A, I have C, and they're somewhere on that plane, and then point B is somewhere not on the plane. So this is like a rendering of what I have. So vectors that are parallel to the plane, well, I have 2 points, and if I have 2 points, I can figure out a vector. The vector going from A to C, that is on the plane, and if I wanted, I could move that around, and that can also be considered parallel to the plane. And likewise, the vector CA, that is also parallel to the plane. All right, so I'm going to go ahead and find, let's do this, AC. So AC is going to be OC minus OA. So these are the position vectors going to point C and A respectively. Okay, so OC, all you have to do is look at the point for C. C is 165. So OC is 165, but with square brackets. Minus OA, which is 1, 3 minus 1. Okay, so 1 minus 1 is 0, 6 minus 3 is 3, 5 minus negative 1 is 5 plus 1, which is 6. So 0, 3, 6. And I do that same thing again, but I look for CA. So CA is going to be OA minus OC. And I mean, you can figure it out from scratch, or you can just see that they're opposite vectors. So that means I have 0, minus 3, minus 6. All right, if two vectors are opposite, that means they're negatives of one another. Right? So AC is equal to negative CA. Now, if B was on the plane as well, then you would have, well, you would have 6 different vectors that you could use. You could use AC, CA, you could use CB, BC, AB, and BA. But B is not on the plane, unfortunately, so we can't use that. All right, hopefully that's okay. Let's move on to the next part. So the next part is going to be a little bit of theory. Okay. All right. In R2, there's 2 ways that you can get a line. Either you get 2 points, or you have a direction vector and a point. So in R2, either of these two things will define a line. Okay, so let me just show you that. Okay, so if you have 2 points, A and B, you can define a line because the line connects those 2 points. You can also define a line by having a single point and a direction vector, right? Because a point, I don't know where the line goes, but if I know the direction it's supposed to be heading, given by M, I now can construct my line in the direction of M and also in the opposite direction of M. And based on these two things, I know that the vector equation of a line is given by r is equal to r0 plus t times m. So r0, again, that's the position vector going from the origin to a point on the line, any point on the line, and m is the direction vector. And so we say that t is an element of the real numbers, t is your parameter, it can be any value. And then finally r goes to any point on the line. Now, if you're working in R3, so third dimension, you can have an infinite number of planes be constructed if you just have a point and a direction vector. So just think about that for a moment. If I have a point and a direction vector, my plane, I mean, it can take any orientation that I want. Right? So if you just have a point and a line, you can take a piece of paper and you can orient it any direction. Right? So imagine my hand is a piece of paper. It can be oriented in any direction and still follow that line and the point, which is connected to the line. So you need a little bit more information to specifically define a plane in the third dimension. So we're going to say that in R3, we need the following. Either you need 3 non-collinear points. Remember, if points are collinear, that means that you can create a straight line with them. And obviously, 2 points, you can always create any straight line. If you have 3 points and they're collinear, that means they're lined up with each other. Okay, so 3 non-collinear points, so that would look something like this. Okay, so the only way to connect all 3 of those points is by drawing a triangle. You cannot obtain them using a straight line. Or you can have 2 non-parallel direction vectors. And a point. This way, if you have 2 non-parallel direction vectors, you can actually span this 2-dimensional space, which is the plane. So I have maybe one direction vector going like this, I have another direction vector going like this, and I have a point somewhere. Right? I need the point because I got to get to the plane in the first place. And then once I have these direction vectors, using any combination, scalar combination of these 2 vectors, I can move to any point along the plane. That's the idea. Okay, now for your plane, so just as we had a vector equation of a line in R2, in R3 we have a vector equation of a plane. And actually this is also the vector equation of a line in R3 as well. Just you have to remember that there's 3 components as opposed to 2. So for the plane we have r is equal to r0, so get to the plane first, and then you can move along it either in one direction or the other. So A and B, these are my direction vectors. So A, B. And then any scalar multiple of those, and I can travel anywhere along the plane. So that's what we're looking at here. And then, of course, you can take that and divide it into its parametric equations. So we've got x is equal to x0 plus t a1 plus s b1. Or I can have y is equal to y0 plus t a2 plus s b2. And finally, z is equal to z0 plus t a3 plus s b3. And if you haven't noticed already, that means we're assuming A has the coordinates a1, comma a2, comma a3, and B has the coordinates b1, comma b2, comma b3. Okay, and the s and t, they're different scalar multiples. Obviously, to get to a certain point that you desire, you wouldn't use the same scalar multiple to both of those direction vectors. You might have to have some different combination of the two. Okay. Let's move on to example number 2. All right, a plane has point, so this is part A, P0, which is 3, 7, 0, and direction vectors A, which is 8, -5, 4, and B, which is 1, -3, -2. Okay, so we have to write the vector and parametric equations of the plane. All right, so we have the minimum amount of information we need to define a vector. We have a point, we have 2 direction vectors. We have to make sure that they are not parallel. And the way you do that is by seeing if they are scalar multiples of each other. Okay, so how do you get from 8 to 1? You divide by 8. -5 divided by 8 is not -3, and 4 divided by -8 is not -2. So we are good. They are not parallel. Okay, so I want to write my general formula first. In general, the equation of a plane, the vector equation of a plane, is r is equal to r0 plus t times vector A plus s times vector B. And that's it. So I just have to plug in r0, that's a position vector going from the origin to a point. And if I know this point, the position vector going to that point has the same coordinates, just with square brackets. So 3, 7, 0 plus t A, which is 8, -5, 4. So that's from here. And then plus s times 1, -3, -2. And that's b. And there you go. Okay, so that's the vector equation of the plane. Now, if you want to get the parametric equations, all you have to do is break that down into its x, y, and z components. Okay, so x, remember r is x, y, z, x, y, z with square brackets. So x is going to be 3 plus 8t plus 1s, or just s. Okay, the y is going to be 7 minus 5t minus 3s. Okay, and finally the z, it's going to be 0. You don't have to write 0 plus. It's going to be 4t minus 2s. And there you go. Okay. So that was part A. We figured out the vector and parametric equations of the plane. Now we're going to determine if a specific point is on this plane. Okay. So part B, determine if the point Q, -10, 8, and that should be -6, is on the plane. Okay, so let's see if this point is on the plane. So just like before, we're going to actually take the equation of the plane and we're going to take that point and sub it in and see what we get. So what we really have here, the equation of the plane is x, y, z, which is r, and that's equal to 3, 7, 0 plus t, 8 minus 5, 4, plus s, 1, -3, -2. Now, if you remember doing these types of problems in 8.1, we only had one parameter to deal with. So one equation, one unknown. Here we have 2 unknowns, so that means we need we're going to actually end up with 3 equations because we have 3 dimensions. So solving these types of problems involving planes, and that's not just true for this section, but the future sections as well in this chapter, they're going to take some time. And you're going to have to be careful when you crunch out your numbers to make sure you don't make needless mistakes. And so we'll do these problems, of course, step by step. All right. So I want to know if this particular point is here. So if that point is on the plane, then that means The position vector should satisfy this equation. The position vector -10, 8, -6. It should satisfy this 370 plus t, 8 minus 5, 4, plus s, 1 minus 3 minus 2. Now again, if you remember how we did this with a straight line, we just had to make sure. So let's say if it was a straight line, forget about the s for a second. What you had to do is make sure that the same value for t was matching the equations for x, y, and z. So the x equation would have been -10 is equal to 3 plus 8t. The y equation would have been 8 is equal to 7 minus 5t, and you would form the z equation too. And you have to make sure that the t values are all the same. Now you have s as well. So you need to have the same t and s value for these 3 points. So what we're going to do is similar to the other one. We are going to create a series of 3 equations, and those are, well, the parametric equations, just with the values on the left side. So we're going to get the parametric equations, plug in -10, 8, and -6 in for x, y, and z, and then we're going to solve for s and t. So let's do that first, and then I'll explain where we're going. So -10, 8, and -6. So -10 is equal to 3 plus 8t plus s. Okay, so 8 is equal to 7 minus 5t minus 3s. Okay, and z is equal to 0 plus 4t minus 2s. Now, having studied mathematics for quite some time now, you should understand that in order to solve an equation with 2 unknowns, you need at least 2 equations. And for our purposes, 2 equations here, it's going to be enough. So I'm going to pick any 2 of these 3 equations, and I'm going to see if I can figure out what s and t are. Now, having found an s and a t value from any combination of 2 of these equations, I will plug that s and t value into the 3rd equation and see if it satisfies that equation. If it does, that means that that point is on the plane. And if it doesn't, then the point is not on the plane. Okay, so I'm just going to simplify these first before I label them equations 1, 2, and 3. I'm just going to get only one term with s, one term with t, and one scalar term. So -10 minus 3, that's -13. So -13 is equal to 8t plus s. That's going to be equation number 1. Next, I have 8 minus 7, that's 1. 1 is equal to -5t minus 3s. That's equation 2. And finally, well, this one's already set up. -6 equals 4t minus 2s. That's equation 3. Again, you need only 2 equations. Pick any 2 and then plug it into the last one. You know, just because it's ordered like this, I'm going to use equations 1 and 2 to solve for s and t, and then plug those values into equation 3. Again, it doesn't matter which order you pick as long as you follow the steps I've outlined. Okay, so starting off with equation 1, I have s is equal to -13 minus 8t. Now I'm going to take equation 1 and I'm going to plug it into equation 2. Okay, so plugging that in, equation 2 is right here. I have 1 is equal to -5t minus 3s. S is right here. So s is -13 minus 8t. So you have to expand this. So 1 is equal to -5t plus 39 plus 24t. Okay, so now you can collect your like terms. Okay, so I have 1 minus 39, that's -38. -5t plus 24, that's 24 minus 5, which is 19. So 19t. 19 times -2 is -38, so t is equal to -2. All right, so there's my t value. Now I'm going to take that and plug it back into equation 1 so I can figure out my s value. So going back to equation 1, s is equal to -13 minus 8t. T is -2. So that's -13 plus 16. 16 minus 13 is 3. So I have s is equal to 3. Now take those 2 values, and if they satisfy equation 3, then the point is on the plane. And if it doesn't, it's not. Okay, so now we have to check 3. Okay, so 3 is right here. -6 is equal to 4t minus 2s. So the left side of this equation is 6. Okay, we're going to investigate the right side here. The right side is 4t minus 2s, which is 4t minus 2s. T is -2, s is 3. 4 times -2 is -8, minus 2 times 3, which is 6. That's minus 14. Minus 14 does not equal -6. And because of that one misstep, that means Q is not on the plane. So since left side does not equal right side, therefore Q, which is the label of the point, is not on the plane. Okay, so that's our final answer. You have to show at least this much work. So I do want to make that clear. You might think of a different way of doing this, or maybe you feel like you can skip steps. You gotta show work. Okay, you don't necessarily have to show the simplification steps. You see, I just directly went from this equation to 1 and this equation to 2. You gotta label them. It's gotta be organized, and it has to step by step show what you're finding with a final valid conclusion. Okay. All right, so we are officially halfway through the lesson. Let's keep going. So we're going to continue with example 2. This is now part C. Part C says find the coordinates of 2 other points on the plane. Oops. Find the coordinates of 2 other points on the plane. All right. So in order to do this, think about how you would have done this before if it was a line. Okay, if you just had a straight line, okay, so instead of having the s here, you just had some position vector with a scalar multiple t times another vector, you would just plug in different values for t. And then you would add up these 2 vectors, and you would get some new vector, which is representing a point on the plane, right? So now, because we have s as well, you just have to find s and t values that you're going to plug in, and then figure out what the corresponding point is going to be. Now you can plug in any value for s and t that you want. That doesn't matter. As long as whatever t value you use, it's the same t value for the x, y, and z dimensions, and whatever s you pick, it doesn't have to be the same as t. It doesn't have to be different. Whatever it happens to be, you multiply it to x, y, and z. So you don't choose different values within the dimensions. Okay, so let's pick values for s and t. Pick values for s and t. All right, so for example, let's pick t is equal to 1 and s is equal to 1. All right, so using our equation, r is equal to 370 plus t times 8 minus 5, 4, plus s times 1 minus 3 minus 2. And I think we said 1 and 1. So that means we're actually just adding these vectors together. So it's going to be 3 plus 8 plus 1. So that's 4 plus 8, which is 12. 7 minus 5 is 2. 2 minus 3 is -1. And finally 0, okay, so that's 4 minus 2, which is 2. So the point would be this representation, but with round brackets. So therefore the point is 12 minus 1, 2. And we can do this again. Okay, so go ahead and pick 2 other values for s and t and try this on your own. I'm going to go ahead and try t is equal to 2 and s is equal to -1. If you want, you can use the same values. Okay, so pause the video if you need. In a couple of moments, I'm going to state what the point should be for these 2 s and t values. Okay, so after having paused the video and working this out, you should obtain that the point with this S and T combination is 18, 0, 10. Okay, so that's part C. Part D. Find the x-intercept of the plane. Well, we actually did something like this earlier in the lesson. We were looking for intercepts, and what I had said was, when you're looking for the intercept, set the other values equal to 0. And so what we're going to do is we're going to set y equal to 0, and we're going to set z equal to 0. Okay, so given our vector equation of the line, it's r equals 3, 7, 0 plus t, 8 minus 5, 4 plus s, 1 minus 3 minus 2. So again, I know that the x-intercept has coordinates of 0 and 0 for y and z. So when I replace this with x, y, z, I'm going to replace it with x, 0, 0. I know that that's the position vector because the point will be x, 0, 0. So that gets set equal to 3, 7, 0 plus t, 8 minus 5, 4, plus s, 1, 3 minus 2. So once again, just like the previous example in part B, we have to come up with a series of 3 equations, 3 unknowns. Except this time, we know for certain that we are looking for the x-intercept. So we have certain values for y and z, which are 0 and 0. So I'm going to create my 3 equations. From 2 of those equations, notably from the y and z dimensions, I'm going to figure out my values for s and t. And then having been given those values, I'll plug it in the parametric equation for x to solve for what the x-intercept is going to be. Okay, so if you didn't follow that, let me just show you quickly what I mean. If I was to create parametric equations, my x equation would look like this. X is equal to 3 plus 8t plus s. Right? And I can do the same thing for y and z as well. And y and z, I'm going to do it in a different color because I'm going to solve these separately. For the y direction, you're going to have y, right, because that would be on the left, y, which is 0, is equal to 7 minus 5t minus 3s. And then for the z direction, you would have 0 is equal to 0 plus 4t minus 2s. All right, so let's actually just rearrange this quickly, and then I'll show you the z direction as well. So z, or in this case, sorry, 7 is equal to 5t plus 3s. So just taking those two terms and bringing them to the other side, and then switching them. Okay, so that will be my equation 1 in the z direction. Again, I'm going to have z is equal to 0, right? So there's the 0 is equal to 0 plus 4t minus 2s. Okay, so then that means I have 4t is equal to 2s. Cancel out 2 from both sides, and you get 2t is equal to s. Okay, so that's going to help us out here. I'm going to call that equation 2. If s is equal to 2t, I'm going to plug that into equation 1 and see if I can simplify that a bit more. Okay, so 2 into 1. So 7 is equal to 5t plus 3s, and s is 2t, based on equation 2. So 7 is equal to, that's going to be 6t on the right. So 5t plus 6t, that's 11t. So t is equal to 7 over 11. Okay, now that we know t, I know that s is twice of that. So going back into equation 2, s is equal to 2 times 7 over 11, which is 14 over 11. Okay, so I have my values for s and t. Take those two values, plug it in the equation for x. So this gets plugged in here, and this gets plugged in here. Okay. So x is equal to 3 plus 8t t plus s. So t is 7 over 11. S is 14 over 11. Okay. 8 times 7 is 56. 56 and 14, right, because you have a common denominator of 11. 56 and 14 makes 70. So I have 3 plus 70 over 11. I have to get a common denominator here, so that's going to be 33 over 11 plus 70 over 11, which is 103 over 11. Okay, that is the x-intercept of the plane. So a little bit more work than what you're used to doing in grade 9, but nonetheless doable. Okay, so that is the last part for example 2. Okay, moving on to example 3. Find the vector and parametric equations of each plane. There will be 2 different examples here. Okay, so for part A, we have a plane with the x-intercept of 2, the y-intercept of 4, and the z-intercept of 5. I want to sketch this out, and you'll see why after we get to a different part of the problem. If I sketch this out, so I've got my z, x, and y axes. All right, so I have my intercepts. I'm going to sketch from 1 to 5. Oh, I'm sorry. I'm going to sketch from 1 to 5 on each of the axes. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So I have A, let's see, I'm going to label point A to be my x-intercept. So that's 2, 0, 0. Okay, the y-intercept is 4. I'm going to call that B. And my z-intercept is 5. I'm going to call that C. All right. So you have this. We're trying to come up with a vector equation of this plane. So if you can imagine, let's actually just connect these. If I were to connect these, I get a triangle. But you got to remember that the plane, what I have been trying to help you understand, the plane to be a piece of paper that's angled in a certain direction in 3-dimensional space, however that paper is oriented. This paper is oriented on a bit of an angle, okay? Even though right now the representation is a triangle, you know that this paper extends infinitely in all different directions. But this is just one cutout of it. All right. In order to figure out the equation of a plane, either I need 3 collinear points, which I do, or I have a point and 2 vectors. Now, the reason why having 3 points is useful is because once you have 3 points, you can create those 2 non-parallel vectors. Okay, so for example, I can use the vectors AC and AB to span the 2-dimensional space. AC and AB span the 2-dimensional space. They are not parallel to each other. I could have just as easily used AC and CB, or AC and BA, or BA and CA. It doesn't matter. Any one of those combination of 2 vectors you would have chosen, they wouldn't be parallel, as long as they're not opposite vectors. Okay, so we need 2 vectors to span R2. They have to span 2-dimensional space. Now, I've used that word before in this lesson. Let me explain to you what that means. Span means it has to be able to reach every single point on that two-dimensional plane, on the two-dimensional space. So if I have two vectors that are parallel, then there's no way that I can move away from that straight line. But if I have a vector that's not parallel with AC, let's say, that means I can move away from AC by using some scalar multiple of AB, whether that's positive or negative and however big it happens to be. Okay, so again, I'm using AC and AB. So AC is given by OC minus OA. Okay, OC is just 0, 0, 5, and OA is 2, 0, 0. All right, so 0 minus 2, that's negative 2, 0 minus 0, and then 5 minus 0, that's 5. Okay, so negative 2, 0, 5, that's vector AC. And now I'm going to get vector AB. So that's OB minus OA. All right, so OB, that's going to be 0, 4, 0 minus OA, 2, 0, 0. 0 minus 2 is negative 2, 4 minus 0 is 4, and 0 minus 0 is 0. So there's AB and there's AC. So we have two vectors that are not parallel and they span the two-dimensional space. The only other ingredient you need is 1 point. And guess what? I have 3 points, so you can pick any one of those that you like. I'm going to go ahead and just pick A, but again, it doesn't matter which one you pick. So therefore, A vector equation of the plane, and I'm saying A vector equation because there are so many, just with this way I've solved it, that you could create. A vector equation of the plane using point A, so R is equal to 2, 0, 0, plus, put one parameter multiplied by one vector, plus another parameter multiplied by the other vector. Okay, so plus t times negative 2, 0, 5, plus s times negative 2, 4, 0. S and t are an element of the real numbers. So there is your vector equation of this plane. Now, the parametric equation, that's the easy part. You've already done the hard work. To get the parametric equation, you just have to divide this into the x, y, and z pieces. So I'm just going to fit that right here, x, y, and z. So x, you're looking at 2 minus 2t minus 2s. For y, let's see, you've got 0, 0, and 4. So y is just equal to 4s. And then for z, you're looking at 5t. And that's it. You've got the vector equation. All right, we are almost done. We just have part B to this problem, and that will conclude 8.2. So last piece, again, we're going to have to find the vector and parametric equations of the plane. So for part B, it's for the plane containing the line, let me write it here, x, y, z equals 0, 3 minus 5 plus t, 6 minus 2 minus 1, and parallel to the line x, y, z is equal to 1, 7 minus 4 plus s, 1 minus 3, 3. Okay, in order to solve this, I really strongly encourage you to draw a picture so you understand what is going on here. All right, so the plane is, I just like to draw it as a flat sheet of paper. So there's my plane. I know that it contains this line, and you know what, just to make it clear for myself, I'm going to call this piece right here L1, and I'm going to call the other piece L2. So lines L1 and L2. Now I know that the plane contains line L1, so I'm just going to draw a line here. I'm going to label it L1. And I know that the plane is parallel to L2. So maybe L2 is something like this. Now I realize I've also drawn L2 parallel to L1. So maybe, let me actually grab some white out. I don't want to do that necessarily, because that's not necessarily the case. Parallel to the plane, it might even look something like this. Okay, so imagine a piece of paper and some kind of vector, my pen being the vector and the paper being the plane. This can be pointing in any direction and it's still parallel to the plane. Okay, it's still never going to cross the plane. There are 360 degrees worth of directions that this arrow could possibly point. So that is just another direction. All right, so the plane contains the line L1 and L2. In order to define the plane, I need a point on the plane and I need two direction vectors that span the plane so that they're not scalar multiples of each other. I already know a point on this plane because I know that the line is on the plane. And that here, that's a point on the line. So if I know a point on the line, therefore I know a point on the plane. So maybe this is the point 0, 3, -5. So therefore I know it's also going to be on the plane. Okay, so I know that for my plane, r is equal to r0 plus t times vector A plus s times vector B. Okay, I already know in r0 that's going to be 0, 3, -5. I just need now two vectors that span the plane. Well, guess what? The direction vector for L1, so the direction vector might be going in this direction, it might be going in the opposite direction, but it is on the plane, so I can use that as one of the vectors to span the plane. So I can call that M1, and that is M1 right here. Okay, so I can use that as one of my vectors. So then I have 6, -2, -1 plugged in here. And this line right here, it has its own direction vector. So we'll call that M2. This, where is it? This is M2. Now M2 might not be on the plane, but if it's parallel to the plane, then that means I can translate that over here and have M2 going in that direction. And this is why I changed the way I drew L2. It is not necessarily parallel to L1. And there is one way to know if they're parallel. If M2 and M1 are parallel, in other words, L2 and L1 are parallel, that means that their direction vectors have to be scalar multiples of each other. So we have to show that as well. Okay, so to go from 6 to 1, we have to divide by 6. To get from -2 to -3, we don't divide by 6. Okay, so we can already see that M1 and M2 are not scalar multiples of each other. So M1 does not equal to a constant times M2, therefore they are non-parallel. That is very important. You have to indicate that. Okay, so that means that I can use this vector as the other direction vector for my plane. 1, -3, 3. So there is a vector equation for my plane. Of course, you need the r on the left. And to get the parametric equations, that's the easy part. I just break this down into x, y, and z. Okay. So for x, I have 0. I don't need to write that. Plus 6t plus s. So s and t are elements of the real numbers. For y, I have 3 minus 2t minus 3s. And for z, I have -5 minus t plus 3s. Okay, and that is it. That concludes lesson 8.2, equations of planes. Stay tuned next time for lesson 8.3.